I will be providing an update on the project entitled Long-Term Hydrological Dynamics of Canada's Largest Watershed, the Mackenzie River Basin, today on behalf of myself and the project team. The project is comprised of members from across the GSC international institutions and the Gwich'in Renewable Resources Board and the Gwich'in Tribal Council Department of Cultural Heritage. Much of the work I'll share with you today has been conducted by two PhD students, Andrei Oleksandrenko, who is a PhD student at the University of Alberta, being supervised by Bill Shattuck, and Anne Nguyen, who is a PhD student at Carleton University, being co-supervised by Professor Tim Patterson and myself. I'd like to acknowledge funding not only from the Environmental Geoscience Program, but also from ArcticNet, NERC, and in-kind contributions from the Gwich'in Renewable Resources Board and Gwich'in Tribal Council. The Mackenzie River Basin is one of the world's largest and most important freshwater ecosystems, and climate change is disproportionately affecting the Mackenzie River Basin and other high northern latitude areas. So this was the impetus for our research. We wanted to understand how climate change has and will affect water quantity and quality in the Mackenzie River Basin. To do this, we are going to examine long-term trends and cycles to develop predictive eco-hydrological models. To date, we have collected 11 peat cores and subsampled these peat cores for various analyses. We've also collected over 100 vegetation samples and depth to water table measurements from 8 sites within and outside of the Gwich'in settlement area. We are analyzing the peats for sequential pyrolysis, mercury, inorganic geochemistry, age dating, stable isotopes, and paleontology, in particular testate amoeba, charcoal, and plant remains. Concurrent with this Western science portion is a traditional knowledge study. This is being led by Trevor Lance and Sharon Snowshoe of the Gwich'in Tribal Council Department of Cultural Heritage, and that work is being funded by ArcticNet, and I'm not going to speak about that work today. Combining the TK and the Western science knowledge, we hope to reconstruct depth water table measurements, fire and vegetation history, chemical change and hydrological change, and synoptic scale climate patterns over millennia that we think might be driving future water quantity and quality change in the Mackenzie River Basin. The 11 peat cores that we've collected are shown here. We have 6 sites from within the Gwich'in settlement area and 2 sites from outside. We've collected some in duplicates. 8 are being used for study. The 4 MAC cores were collected with a purpose-built titanium coring device that was designed by Bill Shattuck and his team at the University of Alberta. These cores were collected by the Gwich'in Renewable Resources Board, and I'll focus today on the results of these cores. Here are photos of this coring device in action. This fieldwork was led by the Gwich'in Renewable Resources Board. The cores were frozen immediately and then shipped to the University of Alberta, where they were subsampled for various analyses. Of the 4 MAC cores, MAC S3 is ompotrophic. We know this from its pH. This is a rain-fed bog. It is ideal for reconstruction of atmospheric metal accumulation. The other sites received input from connected surface waters and/or groundwater. The chronologies are based on a combination of lead-210, cesium-137, and AMS radiocarbon dating. These are the radiocarbon models. All of the radiocarbon dates are based on selected plant macrofossils. Here are the chronologies for the 4 MAC cores that I'll be focusing on today. You can see the MAC S3 core in particular extends back to about 6,000 years BP. I'll show you now some geochemical results. These were produced by Andrei Oleksandrenko from the Swamp Laboratory at the University of Alberta. I'll focus on strontium, yttrium, and lead. Strontium is an indicator of groundwater input. Yttrium is an indicator of mineral matter, dust. And lead in this study is considered as an anthropogenic trace element. Here are the strontium profiles by depth. You can see in green, this is the ompotrophic MAC S3 bog, and as expected, it shows lower strontium concentrations than the other sites. Strontium to yttrium ratios can be used to indicate groundwater versus atmospheric dust input. And again, we can see the MAC S3 core has consistently low groundwater input relative to atmospheric input. Here are the profiles of lead. These are by calendar years BP, modeled age on the y-axis. And we can see highly variable concentrations of lead. Some of these are consistent with known high lead concentrations in Northern Hemisphere cores. For example, the Greenland ice cores record input of lead associated with the onset of lead mining and smelting in the Greek civilization and later Roman civilization. And we can see the introduction of lead to gasoline peaks in all 4 of the cores. The lead to copper ratio can be used to estimate the source of lead because they have different melting points. If the lead to copper ratio is high, the lead is probably from burning of coal, for example, or smelting, and not from dust. This is now by depth. We can see variations in the lead to copper ratios throughout all of the cores. These are fairly consistent with the total lead concentration profiles. Now I'll look at certain trace elements. The ones I've decided to focus on are the ones that are regulated by the Canadian Council Minister of Environment. There are interim soil quality guidelines. These are not for peats, but it's the best approximation. And we can see that chromium is highly variable, but is well below the soil quality guidelines. Copper, we can also see is below the interim soil quality guidelines, but the background for copper and peats in the Northern Hemisphere is only about 1 ppm. So values higher than this can reflect atmospheric input or mineral water interaction. And we see values above this background in all of the cores. Here are the profiles for arsenic. Arsenic behaves quite differently. Increased mobilization of arsenic in peats, predominantly as arsenate, occurs with increasing pH. And we see variability in the profiles of arsenic as well. And lastly, also in cadmium. What we intend to do is combine the chemostratigraphies for the cores. Here's an example from MAC-S3. This is the ambitrophic peat bog. And we can see that there are some consistent profiles for certain trace elements. For example, at the top of the core, lead, copper, cadmium, arsenic, and chromium all increased. And we'll be working to synthesize and interpret these data. We are just getting now the results from mercury analysis. These are from the 2 monoliths that were collected near Inuvik. They are plotted by depth and by age. Age is shown in orange and blue is shown and depth is shown in blue. And we can see an increase in mercury in the top of the core. There's been previous question about what changes in mercury represent in peat cores, because with increasing peat humification, certain elements can become mobile. But it appears that mercury is associated with the relatively stable humic acid portion so that it can confidently document atmospheric input of mercury. Here is the mercury profiles for 3 of the MAC cores. We're still waiting for the results from MAC-S4, and we see in these cores as well, at least in MAC-S2 and MAC-S3, increases in mercury near the top of the core. We intend to synthesize all of the geochemical data with our emerging paleontological data. These are the profiles from plant macrofossils. Plant macrofossils were used for dating, but also for evaluating the evolution of these peat bogs in terms of their ecohydrology. In MAC-S1, we can see that this core, this environment transitioned from a poor fen to a rich fen, for example, by changes from moss into a sedge-dominated environment. Here is the MAC-S2 core. We see changes in water level fluctuation shown by strontium as well as by changes in the vegetation. The MAC-S3 core, as expected, was mostly moss dominated, as this was an ambitrophic bog throughout much of its history. And here's the MAC-S4 core, again showing changes in its ecohydrological development. So I'll end there with some highlights. The PhD student Anne Wynn earlier this year produced a fairly lengthy document that is released as a GSC open file. The project plain language summary, abstract, and conclusions are translated into Gwich'in. So far, the project supported 1 PDF, 2 PhDs, 2 MSCs, and local Gwich'in youth and community members, as well as staff member at the Gwich'in Tribal Council. And our next steps, as mentioned, are to complete the remaining analyses and to synthesize our data. Thank you for your attention.